So I'm going to read the yellow paper. I have a massive headache, so I think I'm just gonna read it. I'm just gonna follow it through. I'm not gonna spend so much time thinking about the formulas and stuff like that. And maybe another day I'll go back to this and try to understand it better. But I think I'm just gonna play and let it go in the speed that it is.
Abstract. The blockchain paradigm when coupled with cryptographically secure transactions has demonstrated its utility through a number of projects, with Bitcoin being one of the most notable ones. Each such project can be seen as a simple application on a decentralized, but singleton, compute resource. We can call this paradigm a transactional singleton machine with shared state. Ethereum implements this paradigm in a generalized manner. Furthermore, it provides a plurality of such resources, each with a distinct state and operating code, but able to interact through a message passing framework with others. We discuss its design, implementation issues, the opportunities it provides, and the future hurdles we envisage. 1. Introduction. With ubiquitous internet connections in most places of the world, global information transmission has become incredibly cheap. Technology-rooted movements like Bitcoin have demonstrated through the power of the default, consensus mechanisms, and voluntary respect of the social contract that it is possible to use the internet to make a decentralized value transfer system that can be shared across the world and virtually free to use. This system can be said to be a very specialized version of a cryptographically secure, transaction-based state machine. Follow-up systems such as Bitcoin adapted as original currency application of the technology into other applications, albeit rather simplistic ones. Ethereum is a project which attempts to build a generalized technology on which all transaction-based state machine concepts may be built. Moreover, it aims to provide to the end developer a tightly integrated end-to-end system for building software on a hitherto unexplored compute paradigm in the mainstream, a trustful object messaging compute framework. 1.1. Driving factors. There are many goals of this project. One key goal is to facilitate transactions between consenting individuals who would otherwise have no means to trust one another. This may be due to geographical separation, interfacing difficulty, or perhaps the incompatibility, incompetence, unwillingness, expense, uncertainty, inconvenience, or corruption of existing legal systems. By specifying a state change system through a rich and unambiguous language, and furthermore architecting systems such that we can reasonably expect that an agreement will be thus enforced autonomously, we can provide a means to this end. Dealings in this proposed system would have several attributes not often found in the real world. The incorruptibility of judgment, often difficult to find, comes naturally from a disinterested algorithmic interpreter. Transparency, or being able to see exactly how a state or judgment came about through the transaction log and rules or instructional codes, never happens perfectly in human-based systems since natural language is necessarily vague. Information is often lacking, and plain old prejudices are difficult to shake. Overall, we wish to provide a system such that users can be guaranteed that no matter with which other individuals, systems, or organizations they interact, they can do so with absolute confidence in the possible outcomes and how those outcomes might come about. 1.2. Previous work. Buterin first proposed the kernel of his work in late November 2013. Though now evolved in many ways, the key functionality of the blockchain with a Turing-complete language and an effectively unlimited intertransaction storage capability remains unchanged. Dwork and Nair provided the first word to the usage of the cryptographic proof of computational expenditure as a means of transmitting a value signal over the internet. The value signal was utilized here as a spam deterrence mechanism rather than any kind of currency, but critically demonstrated the potential for a basic data channel to carry a strong economic signal, allowing the receiver to make a physical assertion without having to rely upon trust. Bad later produced a system in a similar vein. The first example of utilizing the proof of work as a strong economic signal to secure a currency was published et al. In this instance, the token was used to keep peer-to-peer file trading in check, providing consumers with the ability to make micropayments to suppliers for their services. The security model afforded by the proof of work was augmented with digital signatures and a ledger in order to ensure that the historical record couldn't be corrupted and that malicious actors could not spoof payment or unjustly complain about service delivery. 5 years later, Nakamoto introduced another such proof of work secure value token, somewhat wider in scope. The fruits of this project, Bitcoin, became the first widely adopted global decentralized transaction ledger. Other projects built on Bitcoin's success. The altcoins introduced numerous other currencies through alteration to the protocol. Some of the best known are Bitcoin and Bitcoin, discussed by Sprinkle. Other projects sought to take the core value content mechanism of the protocol and repurpose it. Aaron discusses, for example, 1. Ethereum, a security centralized generalized transaction ledger. Berlin version. 2. The Bitcoin project, which aims to provide a decentralized name resolution system. Other projects still aim to build upon the Bitcoin network itself, leveraging the large amount of value placed in the system and the vast amount of computation that goes into the consensus mechanism. The Master Coin project, first proposed by Willet, aims to build a richer protocol involving many additional high-level features on top of the Bitcoin protocol through utilization of a number of auxiliary parts to the core protocol. The Color Coins project, proposed by Rosenfeld et al., takes a similar but more simplified strategy, embellishing the rules of the transaction in order to break the fungibility of Bitcoin's-based currency and allow the creation and tracking of tokens through a special Chrono Wallet protocol-aware piece of software. Additional work has been done in the area with the starting the Decentralization Foundation, Ripple, discussed by Buteller and Heinzen, has sought to create a federated system for currency exchange, effectively creating a new financial clearing system. It has demonstrated that high efficiency gains can be made if the decentralization premise is discarded. Early work on smart contracts has been done by Szabo and Miller. Around the 1990s, it became clear that algorithmic enforcement of agreements could become a significant force in human cooperation. Though no specific system was proposed to implement such a system, it was proposed that the future of law would be heavily affected by such systems. In this light, Ethereum may be seen as a general implementation of such a crypto law system. For a list of terms used in this paper, refer to Appendix A. 2. The blockchain paradigm. Ethereum, taken as a whole, can be viewed as a transaction-based state machine. We begin with the genesis state and incrementally execute transactions to morph it into some current state. It is this current state which we accept as the canonical version of the world of Ethereum. This state can include such information as account balances, reputations, trust arrangements, data pertaining to information of the physical world. In short, anything that can currently be represented by a computer is admissible. Transactions thus represent a valid arc between two states. The valid part is important. There exists far more invalid state changes than valid state changes. Invalid state changes might, for example, be things such as reducing an account balance without an equal and opposite increase elsewhere. A valid state transition is one which comes about through a transaction, formally. +1. Whereas the Ethereum state transition function, in Ethereum, together with our considerably more powerful than any existing comparable system, allows components to carry out arbitrary computation, while allows components to store arbitrary state between transactions. Transactions are collated into blocks. Blocks are chained together using a cryptographic hash as a means of reference. Blocks function as a journal, recording a series of transactions together with the previous block and an identifier for the final state, though do not store the final state itself. That would be far too big. They also punctuate the transaction series with incentives for nodes to mine. This incentivization takes place as a state transition function, adding value to a nominated account. Mining is the process of dedicating effort to bolster one series of transactions over any other potential competitor block. It is achieved thanks to a cryptographically secure proof. This scheme is known as a proof of work and is discussed in detail in section 11.5. Formally, we expand to +1. B. T. Where is the block finalization state transition function? B is its block, which includes a series of transactions among some other components, and is the block level state transition function. This is the basis of the blockchain paradigm, a model that forms the backbone of not only Ethereum, but all decentralized consensus-based transaction systems to date. 2.1. Value. In order to incentivize computation within the network, there needs to be an agreed method for transmitting value. To address this issue, Ethereum has an intrinsic currency, Ether, known also as F and sometimes referred to by the Old English T. The smallest subdenomination of Ether, and thus the one in which all integer values of the currency are counted, is Wei. 1 Ether is defined as being 1018 Wei. There exist other subdenominations of Ether. Multiplier name 10. Wei 1012. Szabo 1015. Finney 1018. Ether. Throughout the present work, any reference to value, in the context of Ether, currency, a balance or a payment, should be assumed to be counted in Wei. 2.2. Which history? Since the system is decentralized and all parties have an opportunity to create a new block on some older pre-existing block, the resultant structure is necessarily a tree of blocks. In order to form a consensus as to which path, from root to leaf through this tree structure, known as the blockchain, there must be an agreed upon scheme. If there is ever a disagreement between nodes as to which root to leaf path down the block tree is the best blockchain, then a fork occurs. This would mean that past a given point in time, multiple states of the system may coexist, some nodes believing one block to contain the canonical transactions, other nodes believing some other block to be canonical, potentially containing radically different or incompatible transactions. This is to be avoided at all costs, as the uncertainty that would ensue would likely kill all confidence in the entire system. The scheme we use in order to generate consensus is a simplified version of the Ghost protocol introduced by Sobolinski and Zotter. This process is described in detail in section 10. Ethereum, a security centralized generalized transaction ledger. Berlin version. 3. Sometimes, a path follows a new protocol from a particular height. This document describes one version of the protocol, namely the Berlin version defined by Bako et al. In order to follow back the history of the path, one must reference multiple versions of this document. Here are the block numbers of protocol updates on the Ethereum main network. Name. First block number. Homestead. 1,150,000 Fenter and Whistle. 2,463,000 FSBURI USDREGON. 2,675,000 Byzantium. 4,370,000 Constantinople. 7,280,000 Petersburg. 7,280,000 Istanbul. 9,069,000 for Glacier. 9,200,000. Berlin. 12,244,000 London. 12,965,000. Throughout Glacier. 13,773,000 for Glacier. 15,050,000. Occasionally actors do not agree on the protocol change, and a permanent fork occurs. In order to distinguish between divergent blockchains, EF155 by Buterin introduced the concept of chain ID, which we denote by, for the Ethereum main network, equals 1-3. Conventions. We use a number of typographical conventions for the formal notation, some of which are quite particular to the present work. The two sets of highly structured, top-level, state values are denoted with bold lowercase Greek letters. They fall into those of world state, which are denoted, and those of machine state. Functions operating on highly structured values are denoted with an uppercase Greek letter. For example, the Ethereum state transition function. For most functions, an uppercase letter is used. For example, C, the general cost function. These may be subscripted to denote specialized variants. For example, store, the cost function for the store operation. For specialized and possibly externally defined functions, we may format as typewriter text. For example, the cake 256 hash function is denoted kek. Also, KEC 512 refers to the cake 512 hash function. Tuples are typically denoted with an uppercase letter E. G. T is used to denote an Ethereum transaction. This symbol may, if accordingly defined, be subscripted to refer to an individual component. For example, T denotes the nonce of said transaction. The form of the subscript is used to denote this type. For example, uppercase subscripts refer to tuples with subscriptable components. Scalars and fixed size byte sequences are denoted with a normal lowercase letter. For example, N is used in the document to denote a transaction nonce. Those with a particularly special meaning may be Greek. For example, the number of items required on the stack for a given operation. Arbitrary length sequences are typically denoted as a bold lowercase letter. For example, O is used to denote the byte sequence given as the output data of a message call. For particularly important values, a bold uppercase letter may be used. Throughout, we assume scalars are non-negative integers and thus belong to the set N. The set of all byte sequences is B, formally defined in Appendix B. If such a set of sequences is restricted to those of a particular length, it is denoted with a subscript. Thus, the set of all byte sequences of length 32 is named B32, and the set of all non-negative integers smaller than 2,256 is named M256. This is formally defined in section 4.3. Square brackets are used to index into and reference individual components or subsequences of sequences. For example, denotes the first item on the machine stack. For subsequences, ellipses are used to specify the intended range, to include elements at both limits. For example, denotes the first 32 items of the machine's memory. In the case of the global state, which is a sequence of accounts, themselves tuples, the square brackets are used to reference an individual account. When considering variants of existing values, we follow the rule that within a given scope for definition, if we assume that the unmodified input value be denoted by the placeholder, then the modified and usually stable value is denoted as, and intermediate values would be, etc. On very particular occasions, in order to maximize readability and only if ambiguous in meaning, we may use alphanumeric subscripts to denote intermediate values, especially those of particular note. When considering the use of existing functions, given a function f, the function f denotes a similar, element-wise version of the function mapping instead between sequences. It is formally defined in section 4.3. We define a number of useful functions throughout. One of the more common is, which evaluates to the last item in the given sequence. X. 4. Blocks, state and transactions. Having introduced the basic concepts behind Ethereum, we will discuss the meaning of a transaction, a block, and the state in more detail. 4.1. World state. The world state is a mapping between addresses and account states. Though not stored on the blockchain, it is assumed that the implementation will maintain this mapping in a modified Merkle-Patricia tree. The tree requires a simple database backend that maintains a mapping of byte arrays to byte arrays. We name this underlying database the state database. This is a number of benefits. Firstly, the root node of this structure is cryptographically dependent on all internal data, and as such its hash can be used as a secure identity for the entire system state. Secondly, being an immutable data structure, it allows any previous state to be recalled by simply altering the root hash accordingly. Since we store all such root hashes in the blockchain, we are able to trivially revert to old states. Ethereum, a security centralized generalized transaction ledger. Berlin version. 4. The account state comprises the following four fields. Nonce, a scalar value equal to the number of transactions sent from this address, or, in the case of accounts with associated code, the number of contract creations made by this account. For account of address and state, this would be formally denoted. Balance, a scalar value equal to the number of way owned by this address, formally denoted. Storage root, a 256-bit hash of the root node of the Merkle-Patricia tree that encodes the storage contents of the account, encoded into the trias mapping from the cake 256-bit hash of the 256-bit integer keys to the RLP encoded 256-bit integer values. The hash is formally denoted. Cody hash, the hash of the EVM code of this account. This is the code that gets executed should this address receive a message call. All such code fragments are contained in the state database under their corresponding hashes for later retrieval. This hash is formally denoted, and thus the code may be denoted as B, given that kek equals. Since we typically wish to refer not to the tri's root hash, but to the underlying set of key value pairs stored within, we define a convenient equivalence. Trie, the collapse function for the set of key value pairs in the trie, L, is defined as the element-wise transformation of the base function L, given as L, RLP, where KB32. Vn. It shall be understood that it is not a physical member of the account and does not contribute to its later serialization. If the Cody hash field is the cake 256 hash of the empty string, that is equals kek, then the node represents a simple account, sometimes referred to as a non-contract account. Thus we may define a world state collapse function L, where P, RLP, this function, L, is used alongside the trie function to provide a short identity of the world state. We assume A equals where V is the account validity function, VX and 256X and 256X B32X B32. An account is empty when it has no code, 0 nonce and 0 balance. Empty equals kek equals 0 equals 0. Even callable pre-compiled contracts can have an empty account state. This is because their account states do not usually contain the code describing its behavior. An account is dead when its account state is non-existent or empty. Dead equals empty 4.2. The transaction. A transaction is a single cryptographically signed instruction constructed by an actor externally to the scope of Ethereum. The sender of a transaction cannot be a contract. While it is assumed that the ultimate external actor will be human in nature, software tools will be used in its construction and dissemination. E of 2718 by Zolt introduced the notion of different transaction types.
I forgot to change the voice. Just a sec.
As of the Berlin version of the protocol, there are two transaction types, 0 and 1. Further, there are two subtypes of transactions, those which result in message calls and those which result in the creation of new accounts with associated code, known informally as contract creation. All transaction types specify a number of common fields. Type, EIP 2718 transaction type, formally T-nonce, a scalar value equal to the number of transactions sent by the sender, formally T-gas price, a scalar value equal to the number of way to be paid per unit of gas for all computation costs incurred as a result of the execution of this transaction, formally T. Gas limit, a scalar value equal to the maximum amount of gas that should be used in executing this transaction. This is paid up front, before any computation is done and may not be increased later, formally T. 2. The 160-bit address of the message calls recipient or, for a contract creation transaction, used here to denote the only member of B, formally T. Value, a scalar value equal to the number of way to be transferred to the message calls recipient or, in the case of contract creation, as an endowment to the newly created account, formally T. R, S, values corresponding to the signature of the transaction and used to determine the sender of the transaction, formally T and T. This is expanded in Appendix F. EIP 2930 transactions also have access list, list of access entries to warm up, formally T. Each access list entry E is a tuple of an account address in a list of storage keys, E. Chain ID, formally T must be equal to the network chain ID beta. Y parity, signature Y parity, formally T. 1. Notably, such tools could ultimately become so causally removed from their human-based initiation or humans may become so causally neutral that there could be a point at which they rightly be considered autonomous agents. E.g. contracts may offer bounties to humans for being sent transactions to initiate their execution. Ethereum, a secure decentralist generalist transaction ledger. Berlin version. 5. Legacy transactions do not have an access list, T equals. While chain ID and Y parity for legacy transactions are combined into a single value. W, a scalar value encoding Y parity and possibly chain ID, formally TT equals 27 plus T or T equals 2 beta plus 35 plus T. Additionally, a contract creation transaction contains in it an unlimited size byte array specifying the EVM code for the account initialization procedure, formally T. In it is an EVM code fragment, it returns the body, a second fragment of code that executes each time the account receives a message call. In it is executed only once at account creation and gets discarded immediately thereafter. In contrast, a message call transaction contains data, an unlimited size byte array specifying the input data of the message call, formally T. Appendix F specifies the function, S, which maps transactions to the sender, and happens through the EXA of the SECP256K1 curve, using the hash of the transaction as the datum to sign. For the present we simply assert that the sender of a given transaction T can be represented with S. L. If T equals 0. If T equals 1 where PT. If T equals T. Otherwise. Here, we assume all components are interpreted by the RLP as integer values, with the exception of the access list T and the arbitrary length byte arrays T and T. T set membership symbol T equals beta. T set membership symbol N256. T set membership symbol N256. T set membership symbol N256. The address hash T is slightly different. It is either a 20-byte address hash or, in the case of being a contract creation transaction, it is the RLP empty byte sequence and thus the member of B. T set membership symbol B20. If T6 equals B. Otherwise. 4.3 The block. The block in Ethereum is the collection of relevant pieces of information, H, together with information corresponding to the comprised transactions, T. And a set of other block headers U that are known to have a parent equal to the present block's parent's parent. The block header contains several pieces of information. Parent hash, the cupcake 256-bit hash of the parent block's header, in its entirety, formally H. Omers hash, the cupcake 256-bit hash of the Omers list portion of this block, formally H. Beneficiary, the 160-bit address to which all fees collected from the successful mining of this block be transferred, formally H. State root, the cupcake 256-bit hash of the root node of the state tree, after all transactions are executed and finalizations applied, formally H. Transactions root, the cupcake 256-bit hash of the root node of the tree structure populated with each transaction in the transactions list portion of the block, formally H. Receipts root, the cupcake 256-bit hash of the root node of the tree structure populated with the receipts of each transaction in the transactions list portion of the block, formally H. Logs bloom, the bloom filter composed from indexable information contained in each log entry from the receipt of each transaction in the transactions list, formally H. Difficulty, a scalar value corresponding to the difficulty level of this block. This can be calculated from the previous block's difficulty level and the timestamp, formally H. Number, a scalar value equal to the number of ancestor blocks. The Genesis block has a number of 0, formally H. Gas limit, a scalar value equal to the current limit.
Remember a while ago, I spent a bunch of time trying to figure out what these things were, but now I already found in another article explaining this, and I took a picture. So, but maybe it's worth going over this again, just so I remember what each thing is.
Parent hash, the cupcake 256-bit hash of the parent block. 4.3 The block. The block in Ethereum is the collection of relevant pieces of information, H, together with information corresponding to the comprised transactions, T. And a set of other block headers U that are known to have a parent equal to the present block's parent's parent. The block header contains several pieces of information. Parent hash, the cupcake 256-bit hash of the parent block's header, in its entirety, formally H. Omers hash, the cupcake 256-bit hash of the Omers list portion of this block, formally H beneficiary, the 160-bit address to which all fees collected from the successful mining of this block be transferred, formally H. State root, the cupcake 256-bit hash of the root node of the state tree, after all transactions are executed and finalizations applied, formally H. Transactions root, the cupcake 256-bit hash of the root node of the tree structure populated with each transaction in the transactions list portion of the block, formally H. Receipts root, the cupcake 256-bit hash of the root node of the tree structure populated with the receipts of each transaction in the transactions list portion of the block, formally H. Logs bloom, the bloom filter composed from indexable information contained in each log entry from the receipt of each transaction in the transactions list, formally H. Difficulty, a scalar value corresponding to the difficulty level of this block. This can be calculated from the previous block's difficulty level and the timestamp, formally H. Number, a scalar value equal to the number of ancestor blocks. The genesis block has a number of 0, formally H. Gas limit, a scalar value equal to the current limit of gas expenditure per block, formally H. Gas used, a scalar value equal to the total gas used in transactions in this block, formally H. Timestamp, a scalar value equal to the reasonable output of Unix's time at this block's inception, formally H. Extra data, an arbitrary byte array containing data relevant to this block. This must be 32 bytes or fewer, formally H. Mix hash, a 256-bit hash which, combined with the nonce, proves that a sufficient amount of computation has been carried out on this block, formally H. Nonce, a 64-bit value which, combined with the mihash, proves that a sufficient amount of computation has been carried out on this block, formally H. The other two components in the block are simply a list of Omer block headers, B, and a series of the transactions, B. Formally, we can refer to a block B. B. Omer is a gender-neutral term to mean sibling of parent, C. Ethereum, a secure decentralist generalist transaction ledger. Berlin version 6. 4.3.1 Transaction receipt. In order to encode information about a transaction concerning which it may be useful to form a zero-knowledge proof, or index, and search, we encode a receipt of each transaction containing certain information from its execution. Each receipt, denoted B for the ith transaction, is placed in an index-keyed tree and the root recorded in the header as H. The transaction receipt, R, is a tuple of 5 items comprising the type of the transaction, R, the status code of the transaction, R, the cumulative gas used in the block containing the transaction receipt as of immediately after the transaction has happened, R. The set of logs created through execution of the transaction, R, and the bloom filter composed from information in those logs, R. R is equal to the type of the corresponding transaction. The function L prepares a transaction receipt for being transformed into an RLP serial least byte array. L. We assert that the status code R is a non-negative integer. R set membership symbol N. We assert that R, the cumulative gas used, is a non-negative integer and that the logs bloom, R, is a hash of size 2048 bits. R set membership symbol N. R set membership symbol B256. The sequence R is a series of log entries. A log entry, O, is a tuple of the logger's address, O, a possibly empty series of 32-byte log topics, O, and some number of bytes of data, O. O set membership symbol B20. Turned X set membership symbol O, X set membership symbol B32. O set membership symbol B. We define the bloom filter function, M, to reduce a log entry into a single 256-byte hash. M set membership symbol. Union set symbol. Where M3:2048 is a specialized bloom filter that sets 3 bits out of 2048, given an arbitrary byte sequence. It does this through taking the low-order 11 bits of each of the first 3 pairs of bytes in a cupcake 256 hash of the byte sequence. Formally, M3:2048Y, Y set membership symbol B256. Where Y equals accept. Turned I set membership symbol B2047. I equals 1. MCAC mod 2048. Where B is the bit reference function such that B equals the bit of index J in the byte array X. Notably, it treats X as big endian. 4.3.2 Holistic validity. We can assert a block's validity if and only if it satisfies several conditions. It must be internally consistent with the Omer and transaction block hashes and the given transactions B, when executed in order on the base state sigma. Result in a new state of the identity H. H. Tree. H. Kick. H.
I don't understand
Tree.
the symbols here.
H. Tree. HB. Where P and P are pairwise RLP transformations, but with a special treatment for EIP 2718 transactions. P, RLP. If T equals 0. RLP, otherwise, and P, RLP. If R equals 0. RLP, otherwise. Furthermore, tree equals P. Thus tree is the root node hash of the Merkle-Patricia tree structure containing the key value pairs of the state sigma with values encoded using RLP, and P is the parent block of B, defined directly. The values stemming from the computation of transactions, specifically the transaction receipts, B, and that defined through the transaction state accumulation function, pi, are formalized later in section 11.4. 4.3.3 Serialization. The function L and L are the preparation functions for a block and block header respectively. We assert the types and order of the structure for when the RLP transformation is required. L, where L takes a special care of EIP 2718 transactions. L equals L. If T equals 0. RLP, otherwise with L and L being element-wise sequence transformations, thus. f, for any function f. 2048 equals 211, and the low order 11 bits is the modulo 2048 of the operand, which is in this case is each of the first 3 pairs of bytes in a cupcake 256 hash of the byte sequence. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 7. The component types are defined thus. HP set membership symbol B32. HO set membership symbol B32. HC set membership. We now have a rigorous specification for the construction of a formal block structure. The RLP function RLP provides the canonical method for transforming this structure into a sequence of bytes ready for transmission over the wire or storage locally. 4.3.4 Block header validity. We define P to be the parent block of B, formally. PB, kek, equals H. The block number is the parent's block number incremented by 1. H5 plus 1. The canonical difficulty of a block of header H is defined as D. D234. If H equals 0 max HD plus X times final sigma plus, otherwise where? Min 217. XPHD 2048. Final sigma max HS 9. 99. Y1 if P equals 0 2 otherwise. 2BH100000C2. H max. Kappa. The Homestead difficulty parameter, final sigma, is used to affect a dynamic homeostasis of time between blocks, as the time between blocks varies, as discussed below, as implemented in EIP2 by Buterin. In the Homestead release, the exponential difficulty symbol causes the difficulty to slowly increase at an exponential rate, and thus increasing the block time difference, and putting time pressure on transitioning to proof of stake. This effect, known as the difficulty bomb, or ice age, was explained in EIP 649 by Skoeden and Buterin and delayed and implemented earlier in EIP2. Final sigma was also modified in EIP 100 with the use of x, the adjustment factor above, and the denominator 9, in order to target the mean block time including uncle blocks by Buterin. In the Byzantium release, with EIP 649, the ice age was delayed by creating a fake block number, h, which is obtained by subtracting 3 million from the actual block number, which in other words reduced and the time difference between blocks, in order to allow more time to develop proof of stake and preventing the network from freezing up. Subsequently, EIP 1234 by Skoeden, EIP 2384 by Connor, EIP 3554 by Hancock, EIP 4345 by Byko et al., and EIP 5133 by Stangzak et al. Increased the subtrahend kappa. The canonical gas limit h of a block of header h must fulfill the relation h. HPHL PHL 1024 H 5000. H is the timestamp of block H and must fulfill the relation HPHS. This mechanism enforces a homeostasis in terms of the time between blocks. A smaller period between the last two blocks results in an increase in the difficulty level and thus additional computation required, lengthening the likely next period. Conversely, if the period is too large, the difficulty, and expected time to the next block, is reduced. The nonce, H, must satisfy the relations N6 2256 H. M equals H. With equals pow. Where Hn is the new block's header H, but without the nonce and mix hash components, D being the current DAG, a large data set needed to compute the mix hash, and pow is the proof of work function, see section 11. 5. This evaluates to an array with the first item being the mix hash, to prove that a correct DAG has been used, and the second item being a pseudo-random number cryptographically dependent on H and D. Given an approximately uniform distribution in the range 0, 200, and 64, the expected time to find a solution is proportional to the difficulty, H. This is the foundation of the security of the blockchain and is the fundamental reason why a malicious node cannot propagate newly created blocks that would otherwise overwrite history. Because the nonce must satisfy this requirement, and because its satisfaction depends on the contents of the block and in turn its composed transactions, creating new, valid, blocks is difficult and Ethereum, a secure decentralized generalist transaction ledger. Berlin version 8. Over time, requires approximately the total compute power of the trustworthy portion of the mining peers. Thus we are able to define the block header validity function V. VN6 2256 HM equals H. H equals DH less than or equal to H. HPHL PHL 1024 H5000 HPHS. H equals 5 plus 1. H less than or equal to 32. Where equals pow. Noting additionally that extra data must be at most 32 bytes. 5. Gas and payment. In order to avoid issues of network abuse and to sidestep the inevitable questions stemming from Turing completeness, all programmable computation in Ethereum is subject to fees. The fee schedule is specified in units of gas. Thus any given fragment of programmable computation has a universally agreed cost in terms of gas. Every transaction has a specific amount of gas associated with it, gas limit. This is the amount of gas which is implicitly purchased from the sender's account balance. The purchase happens at the according gas price, also specified in the transaction. The transaction is considered invalid if the account balance cannot support such a purchase. It is named gas limit since any unused gas at the end of the transaction is refunded to the sender's account. Gas does not exist outside of the execution of a transaction. Thus for accounts with trusted code associated, a relatively high gas limit may be set and left alone. In general, ether used to purchase gas that is not refunded is delivered to the beneficiary address, the address of an account typically under the control of the miner. Transactors are free to specify any gas price that they wish, however miners are free to ignore transactions as they choose. A higher gas price on a transaction will therefore cost the sender more in terms of ether and deliver a greater value to the miner and thus will more likely be selected for inclusion by more miners. Miners, in general, will choose to advertise the minimum gas price for which they will execute transactions, and transactors will be free to canvass these prices in determining what gas price to offer. Since there will be a distribution of minimum acceptable gas prices, transactors will necessarily have a trade-off to make between lowering the gas price and maximizing the chance that their transaction will be mined in a timely manner. 6. Transaction execution. The execution of a transaction is the most complex part of the Ethereum protocol. It defines the state transition function upsilon. It is assumed that any transactions executed first pass the initial tests of intrinsic validity. These include: the transaction is well-formed RLP, with no additional trailing bytes. The transaction signature is valid. The transaction nonce is valid. The sender account has no contract code deployed. The gas limit is no smaller than the intrinsic gas, G, used by the transaction, and the sender account balance contains at least the cost, V, required in upfront payment. Formally, we consider the function upsilon, with T being a transaction and sigma the state. Sigma equals upsilon. Thus sigma is the post-transactional state. We also define upsilon to evaluate to the amount of gas used in the execution of a transaction, upsilon to evaluate to the transaction's accrued log items, and upsilon to evaluate to the status code resulting from the transaction. These will be formally defined later. 6.1 Substate. Throughout transaction execution, we accrue certain information that is acted upon immediately following the transaction. We call this the accrued transaction substate, or accrued substate for short, and represent it as A, which is a tuple. A. The tuple contents include A, the self-destruct set, a set of accounts that will be discarded following the transaction's completion. A is the log series. This is a series of archived and indexable checkpoints in VM code execution that allow for contract calls to be easily tracked by onlookers external to the Ethereum world. A is the set of touched accounts, of which the empty ones are deleted at the end of a transaction. A is the refund balance, increased through using the store instruction in order to reset contract storage to 0 from some non-zero value. Though not immediately refunded, it is allowed to partially offset the total execution costs. Finally, EIP 2929 by Buterin and Swend introduced A, the set of accessed account addresses, and A, the set of accessed storage keys. We define the empty accrued substate A to have no self-destructs, no logs, no touched accounts, 0 refund balance, all precompiled contracts in the accessed addresses, and no accessed storage. A, 0, pi, where pi is the set of all precompiled addresses. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 9. 6.2 Execution. We define intrinsic gas G, the amount of gas this transaction requires to be paid prior to execution, as follows. G. I set membership symbol TT. Stat 0. If I equals 0 tan on 0. Where T means the series of bytes of the transaction's associated data and initialization EVM code, depending on whether the transaction is for contract creation or message call. Create is added if the transaction is contract creating, but not if a result of EVM code. Gauch list address and Gauch list storage are the costs of warming up account and storage access, respectively. G is fully defined in Appendix G. The upfront cost V is calculated as VTT plus T. The validity is determined as S6 equals sigma equals kek T equals sigma G0. Note the final condition, the sum of the transaction's gas limit, T, and the gas utilized in this block prior, given by, must be no greater than the block's gas limit, BHL. Also, with a slight abuse of notation, we assume that sigma equals kek, sigma equals 0, and sigma equals 0 if sigma equals. The execution of a valid transaction begins with an irrevocable change made to the state. The nonce of the account of the sender, S, is incremented by 1 and the balance is reduced by part of the upfront cost, TT. The gas available for the preceding computation, G, is defined as TG. The computation, whether contract creation or a message call, results in an eventual state, the change to which is deterministic and never invalid. There can be no invalid transactions from this point. We define the checkpoint state sigma. Sigma. Sigma except. Sigma. Sigma TT. Sigma. Sigma plus 1. Evaluating sigma from sigma depends on the transaction type, either contract creation or message call. We define the tuple of post-execution provisional state sigma, remaining gas G. Accrued substate A and status code Z. Lambda, S, G. T, 0. If T equals theta, S, T. T, G, T, 0, otherwise. Where A except A union set symbol, and G is the amount of gas remaining after deducting the basic amount required to pay for the existence of the transaction. GTG. Note we use theta 4 and lambda 4 to denote the fact that only the first 4 components of the function's values are taken. The final represents the message call's output value and is unused in the context of transaction evaluation. After the message call or contract creation is processed, the refund counter has to be incremented for the accounts that were self-destruct throughout its invocation. A plus. I set membership symbol A. R self-destruct. Then the state is finalized by determining the amount to be refunded, G from the remaining gas, G, plus some allowance from the refund counter, to the sender at the original rate. GG plus min. The total refundable amount is the legitimately remaining gas G, added to A, with the latter component being capped up to a maximum of half of the total amount used TG. Therefore, G is the total gas that remains after the transaction has been executed. The ether for the gas is given to the miner, whose address is specified as the beneficiary of the present block B. So we define the pre-final state sigma in terms of the provisional state sigma. 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 Except sigma. Sigma plus GT. Sigma. The final state, sigma, is reached after deleting all accounts that either appear in the self-destruct set or are touched in empty. Sigma sigma. Turned AI set membership symbol A, sigma equals if DEAD, and finally, we specify upsilon, the total gas used in this transaction, upsilon, the logs created by this transaction, and Ethereum, a secure decentralized generalist transaction ledger. Berlin version 10. Upsilon, the status code of this transaction, upsilon TG. Upsilon A. Upsilon Z. These are used to help define the transaction receipt and are also used later for state and nonce validation. 7. Contract creation. There are a number of intrinsic parameters used when creating an account: sender, original transactor, available gas, gas price, endowment, together with an arbitrary length byte array, I, the initialization EVM code, the present depth of the message call / contract creation stack, the salt for new account's address, and finally the permission to make modifications to the state. The salt zeta might be missing, formally. Zeta set membership symbol B32 union set symbol B. If the creation was caused by create2, then zeta 6 equals. We define the creation function formally as the function lambda, which evaluates from these values, together with the state sigma and the accrued substate A, to the tuple containing the new state, remaining gas, new accrued substate, status code, and output. Lambda, the address of the new account, is defined as being the rightmost 160 bits of the cupcake 256 hash of the RLP encoding of the structure containing only the sender and the account nonce. For create2, the rule is different and is described in EIP 1014 by Buterin. Combining the two cases, we define the resultant address for the new account A address B 96.255 LRLP. If zeta equals S zeta kek otherwise, where is the concatenation of byte arrays, BA?
I think I'm gonna briefly stop to look at the OP code.
S zeta kek otherwise, where is the concatenation of byte arrays, BA? .b evaluates to a binary value containing the bits of indices in the range of the binary data x, and sigma is the address state of x, or if none exists. Note we use one fewer than the sender's nonce value. We assert that we have incremented the sender account's nonce prior to this call, and so the value used is the sender's nonce at the beginning of the responsible transaction or VM operation. The address of the new account is added to the set of accessed accounts. A except A union set symbol. The account's nonce is initially defined as 1, the balance as the value passed, the storage is empty, and the code hash is the cupcake 256-bit hash of the empty string. The sender's balance is also reduced by the value passed. Thus the mutated state becomes sigma. Sigma sigma except sigma equals kek. Sigma equals if sigma equals v equals 0a. Otherwise a, where v is the account's pre-existing value, in the event it was previously in existence. v0. If sigma equals sigma. Otherwise. Finally, the account is initialized through the execution of the initializing EVM code I according to the execution model. Code execution can affect several events that are not internal to the execution state. The account's storage can be altered, further accounts can be created, and further message calls can be made. As such, the code execution function psi evaluates to a tuple of the resultant state sigma, available gas remaining g, the resultant accrued substate A, and the body code of the account O. Psi. Where I contains the parameters of the execution environment, that is I, A, I, O, I, P, I evaluates to the empty tuple as there is no input data to this call. I has no special treatment and is determined from the blockchain. Code execution depletes gas, and gas may not go below 0, thus execution may exit before the code has come to a natural halting state. In this exceptional cases we say an out-of-gas exception has occurred. The evaluated state is defined as being the empty set, and the entire create operation should have no effect on the state, effectively leaving it as it was immediately prior to attempting the creation. If the initialization code completes successfully, a final contract creation cost is paid, the code deposit cost, C, proportional to the size of the created contract's code. See code deposit times O. If there is not enough gas remaining to pay this, i.e. G, the gas remaining will be 0 in any such exceptional condition, i.e. if the creation was conducted as the reception of a transaction, then this doesn't affect payment of the intrinsic cost of contract creation, it is paid regardless. However, the value of the transaction is not transferred. For which can differ from the sender in the case of a message call or contract creation not directly triggered by a transaction but coming from the execution of EVM code. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 11. to the aborted contract's address when we are out of gas, thus the contract's code is not stored. If such an exception does not occur, then the remaining gas is refunded to the originator and the now altered state is allowed to persist. Thus formally, we may specify the resultant state, gas, accrued substate, and status code is where G0. If FGC otherwise. Sigma. Sigma. If F sigma equals sigma. Except sigma equals. If dead. Sigma. Except sigma equals kek otherwise. AA. The exception in the determination of sigma dictates that O, the resultant byte sequence from the execution of the initialization code, specifies the final body code for the newly created account. Note that intention is that the result is either a successfully created new contract with its endowment, or no new contract with no transfer of value. In addition, observe that if the execution of the initializing code reverts, the resultant gas G is not depleted, but no new account is created. 7.1 Subtleties. Note that while the initialization code is executing, the newly created address exists but with no intrinsic body code. Thus any message call received by it during this time causes no code to be executed. If the initialization execution ends with a self-destruct instruction, the matter is moot since the account will be deleted before the transaction is completed. For a normal stop code, or if the code returned is otherwise empty, then the state is left with a zombie account, and any remaining balance will be locked into the account forever. 8. Message call. In the case of executing a message call, several parameters are required: sender, transaction originator, recipient, the account whose code is to be executed, available gas, value and gas price together with an arbitrary length byte array, D. The input data of the call, the present depth of the message call / contract creation stack, and finally the permission to make modifications to the state. Aside from evaluating to a new state in accrued transaction substate, message calls also have an extra component, the output data denoted by the byte array O. This is ignored when executing transactions, however message calls can be initiated due to VM code execution, and in this case this information is used. Thetan note that we need to differentiate between the value that is to be transferred, V, from the value apparent in the execution context, V, for the delegate call instruction. We define sigma, the first transitional state, as the original state but with the value transferred from sender to recipient. Sigma sigma plus V sigma V unless S equals R. Throughout the present work, it is assumed that if sigma was originally undefined, it will be created as an account with no code or state and zero balance in nonce. Thus the previous equation should be taken to mean sigma sigma except sigma if sigma equals V equals 0 A otherwise A, and sigma sigma except sigma kek if sigma equals V6 equals 0, sigma if sigma equals V equals 0, sigma A otherwise A. The account's associated code is executed according to the execution model. Just as with contract creation, if the execution halts in an exceptional fashion, then no gas is refunded to the caller and the state is reverted to the point immediately prior to balance transfer. During initialization code execution, fixed code size on the address should return 0, which is the length of the code of the account, while code size should return the length of the initialization code. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 12. Sigma sigma. If sigma equals sigma otherwise G 0. If sigma equals O equals G otherwise AA. If sigma equals A. It is assumed that the client will have stored the pair I at some point prior in order to make the determination of I feasible. As can be seen, there are 9 exceptions to the usage of the general execution framework SI for evaluation of the message call. These are so-called precompiled contracts, meant as a preliminary piece of architecture that may later become native extensions. The contracts in addresses 1 to 9 execute the elliptic curve public key recovery function, the SHA-2 256-bit hash scheme, the RIPAMD 160-bit hash scheme, the identity function, arbitrary precision modular exponentiation, elliptic curve addition, elliptic curve scalar multiplication, an elliptic curve pairing check, and the Blake 2 compression function F respectively. Their full formal definition is in Appendix E. We denote the set of the addresses of the precompiled contracts by pi. 9 Execution model. The execution model specifies how the system state is altered given a series of bytecode instructions in a small tuple of environmental data. This is specified through a formal model of a virtual state machine, known as the Ethereum virtual machine. It is a quasi-Turing complete machine. The quasi-qualification comes from the fact that the computation is intrinsically bounded through a parameter, gas, which limits the total amount of computation done. 9.1 Basics. The EVM is a simple stack-based architecture. The word size of the machine is 256-bit. This was chosen to facilitate the cupcake 256 hash scheme and elliptic curve computations. The memory model is a simple word-addressed byte array. The stack has a maximum size of 1024. The machine also has an independent storage model. This is similar in concept to the memory, but rather than a byte array, it is a word-addressable word array. Unlike memory, which is volatile, storage is non-volatile and is maintained as part of the system state. All locations in both storage and memory are well-defined initially as 0. The machine does not follow the standard von Neumann architecture. Rather than storing program code in generally accessible memory or storage, it is stored separately in a virtual ROM interactable only through a specialized instruction. The machine can have exceptional execution for several reasons, including stack underflows and invalid instructions. Like the out-of-gas exception, they do not leave state changes intact. Rather, the machine halts immediately and reports the issue to the execution agent, which will deal with it separately. 9.2 Fees Overview. Fees are charged under 3 distinct circumstances, all 3 as prerequisite to the execution of an operation. The first and most common is the fee intrinsic to the computation of the operation. Secondly, gas may be deducted in order to form the payment for a subordinate message call or contract creation. This forms part of the payment for create to, call and call code. Finally, gas may be paid due to an increase in the usage of the memory. Over an account's execution, the total fee for memory usage payable is proportional to smallest multiple of 32 bytes that are required, such that all memory indices are included in the range. This is paid for on a just-in-time basis. As such, referencing an area of memory at least 32 bytes greater than any previously indexed memory will certainly result in an additional memory usage fee. Due to this fee, it is highly unlikely addresses will ever go above 32-bit bounds. That said, implementations must be able to manage this eventuality. Storage fees have a slightly nuanced behavior to incentivize minimization of the use of storage. The execution fee for an operation that clears an entry in the storage is not only waived, a qualified refund is given, in fact. This refund is effectively paid upfront since the initial usage of a storage location costs substantially more than normal usage. See Appendix H for a rigorous definition of the EVM gas cost. Ethereum, a secure decentralized generalist transaction ledger. Berlin version. 13. 9.3 Execution environment. In addition to the system state sigma, the remaining gas for computation G, and the accrued substate A, there are several pieces of important information used in the execution environment that the execution agent must provide. These are contained in the tuple I. The address of the account which owns the code that is executing. I. The sender address of the transaction that originated this execution. I. The price of gas in the transaction that originated this execution. I. The byte array that is the input data to this execution. If the execution agent is a transaction, this would be the transaction data. I. The address of the account which caused the code to be executing. If the execution agent is a transaction, this would be the transaction sender. I. The value, in way, passed to this account as part of the same procedure as execution. If the execution agent is a transaction, this would be the transaction value. I. The byte array that is the machine code to be executed. I. The block header of the present block. I. The depth of the present message call or contract creation S being executed at present. I. The permission to make modifications to the state. The execution model defines the function psi, which can compute the resultant state sigma, the remaining gas G, the resultant accrued substate A and the resultant output, O, given these definitions. For the present context, we will define it as psi, where we will remember that A, the accrued substate, is defined in section 6.1. 9.4 Execution Overview. We must now define the psi function. In most practical implementations, this will be modeled as an iterative progression of the pair comprising the full system state, sigma, and the machine state, mu. Formally, we define it recursively with the function x. This uses an iterator function O together with function z, which determines if the present state is an exceptional halting state of the machine, and h, specifying the output data of the instruction if and only if the present state is a normal halting state of the machine. The empty sequence, denoted, is not equal to the empty set, denoted. This is important when interpreting the output of h, which evaluates to when execution is to continue but a series when execution should halt. Psi x mu g. Note that, when we evaluate psi, we drop the fourth element I and extract the remaining gas mu from the resultant machine state. Mu x is thus cycled until either z becomes true, indicating that the present state is exceptional and that the machine must be halted, and any change is discarded, or until h becomes a series, indicating that the machine has reached a controlled halt. 9.4.1 Machine state. The machine state mu is defined as the tuple which are the gas available, the program counter PC set membership symbol N256, the memory contents, the active number of words in memory, and the stack contents. The memory contents mu are a series of zeros of size 2256. For the ease of reading, the instruction mnemonics, written in small caps, should be interpreted as their numeric equivalents. The full table of instructions and their specifics is given in Appendix H. For the purposes of defining Z, H, and O, we define W as the current operation to be executed. W if mu PC. Otherwise, we also assume the fixed amounts of delta and alpha, specifying the stack items removed and added, both subscriptable on the instruction and an instruction cost function C evaluating to the full cost, in gas, of executing the given instruction. Ethereum, a secure decentralized generalist transaction ledger. Berlin version. 14. 9.4.2 Exceptional halting. The exceptional halting function Z is defined as Z mu delta equals mu W equals jumpy mu 6 equals 0 mu slash set membership symbol D. This states that the execution is in an exceptional halting state if there is insufficient gas, if the instruction is invalid, if there are insufficient stack items, if a jump slash jumpy destination is invalid. The new stack size would be larger than 1024 or state modification is attempted during a static call. The astute reader will realize that this implies that no instruction can, through its execution, cause an exceptional halt. Also, the execution is in an exceptional halting state if the gas left prior to executing an store instruction is less than or equal to the call stipend. See EIP 2200 by Tang for more information. 9.4.3 Jump destination validity. We previously used D as the function to determine the set of valid jump destinations given the code that is being run. We define this as any position in the code occupied by a jump dest instruction. All such positions must be on valid instruction boundaries, rather than sitting in the data portion of push operations, and must appear within the explicitly defined portion of the code. Formally, D where D if I C union set symbol D if C equals jump dest. D. Otherwise, where n is the next valid instruction position in the code, skipping the data of a push instruction, if any. N. I plus W push 1 plus 2. If W set membership symbol. I plus 1. Otherwise. 9.4.4 Normal halting. The normal halting function h is defined. H. Return if W set membership symbol. If W set membership symbol. Otherwise. The data returning halt operations, return and revert, have a special function return. Note also the difference between the empty sequence and the empty set as discussed here. 9.5 The execution cycle. Stack items are added or removed from the leftmost, lower indexed portion of the series, all other items remain unchanged. O. Alpha delta. Mu mu plus. Turned AX set membership symbol mu. The gas is reduced by the instruction's gas cost, and for most instructions, the program counter increments on each cycle. For the 3 exceptions, we assume a function j, subscript by one of 2 instructions, which evaluates to the according value. Mu. Mu c. Mu pc. JJUMP if W equals jump J jumpy if W equals jumpy and otherwise. In general, we assume the memory, accrued substate, and system state do not change. Mu m. Mu m. Mu I. Mu I. AA. Sigma sigma. However, instructions do typically alter one or several components of these values. Altered components listed by instruction are noted in Appendix H, alongside values for alpha and delta and a formal description of the gas requirements. 10 Block tree to blockchain. The canonical blockchain is a path from root to leaf through the entire block tree. In order to have consensus over which path it is, conceptually we identify the path that has had the most computation done upon it, or the heaviest path. Clearly, one factor that helps determine the heaviest path is the block number of the leaf, equivalent to the number of blocks, not counting the unmined genesis block, in the path. The longer the path, the greater the total mining effort that must have been done in order to arrive at the leaf. This is akin to existing schemes, such as that employed in Bitcoin-derived protocols. Since a block header includes the difficulty, the header alone is enough to validate the computation done. Any block contributes toward the total computation or total difficulty of a chain. Ethereum, a secure decentralist generalist transaction ledger. Berlin version. 15. Thus we define the total difficulty of block B recursively as BB plus B. BP. As such, given a block B, B is its total difficulty, B is its parent block and B is its difficulty. 11 Block finalization. The process of finalizing a block involves 4 stages. Validate OMRs. Validate transactions. Apply rewards. Verify state and block nonce. 11.1 OMR validation. The validation of OMR headers means nothing more than verifying that each OMR header is both a valid header and satisfies the relation of nth generation OMR to the present block where n less than or equal to 6. The maximum of OMR headers is 2. Formally. B62. U set membership symbol B. VK, 6, where K denotes the is-kin property. K. False. If n equals 0 s. K, n1, otherwise ns denotes the is-sibling property. S equals ph6 equals uu slash set membership symbol B, where B and P are the block and the parent block of the corresponding header H respectively. 11.2 Transaction validation. The given gas used must correspond faithfully to the transactions listed, BHG. The total gas used in the block must be equal to the accumulated gas used according to the final transaction. BHG equals 11.3 Reward application. The application of rewards to a block involves raising the balance of the accounts of the beneficiary address of the block in each OMR by a certain amount. We raise the block's beneficiary account by block. For each OMR, we raise the block's beneficiary by an additional 132 of the block reward, and the beneficiary of the OMR gets rewarded depending on the block number. Formally, we define the function omega. Omega sigma, sigma equals sigma except sigma equals sigma plus reblock. Turned a U set membership symbol B. Sigma equals if sigma equals R equals 0 A otherwise A. R, reblock. If there are collisions of the beneficiary addresses between OMRs and the block, additions are applied cumulatively. We define the block reward in way. Reblock equals 1018 times 5 if H. 3 if F Byzantium 6 HF Constantinople. 11.4 State and nonce validation. We may now define the function, gamma, that maps a block B to its initiation state. Gamma sigma. If P equals sigma, tree, equals PHR. Otherwise here, tree, means the hash of the root node of a tree of state sigma. It is assumed that implementations will store this in the state database, which is trivial and efficient since the tree is by nature an immutable data structure. And finally we define phi, the block transition function, which maps an incomplete block B to a complete block B, phi B equals B. Except B equals N6 2256 H. B equals M with equals PO WB. B except B equals R, B. With D being a data set as specified in Appendix J. As specified at the beginning of the present work, pi is the state transition function, which is defined in terms of omega, the block finalization function, and upsilon, the transaction evaluation function, both now well defined. As previously detailed, R and R are the nth corresponding status code, logs, and cumulative gas used after each transaction. We also define the nth state sigma, which is defined simply as the state resulting from applying the corresponding transaction to the state resulting from the previous transaction. Sigma equals gamma. If n Upsilon. Otherwise, in the case of B, we take a similar approach, defining each item as the gas used in evaluating the corresponding transaction summed with the previous item, giving us a running total. R equals 0 if n upsilon plus r. Otherwise, for r, we utilize the upsilon function that we conveniently defined in the transaction execution function. R equals upsilon. We define r in a similar manner. R equals upsilon. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 16. Finally, we define pi as the new state given the block reward function omega applied to the final transaction's resultant state. Pi omega. Thus the complete block transition mechanism is defined, except for POW, the proof of work function. 11.5 Mining proof of work. The mining proof of work exists as a cryptographically secure nonce that proves beyond reasonable doubt that a particular amount of computation has been expended in the determination of some token value n. It is utilized to enforce the blockchain security by giving meaning and credence to the notion of difficulty. However, since mining new blocks comes with an attached reward, the proof of work not only functions as a method of securing confidence that the blockchain will remain canonical into the future, but also as a wealth distribution mechanism. For both reasons, there are two important goals of the proof of work function. Firstly, it should be as accessible as possible to as many people as possible. The requirement of, or reward from, specialized and uncommon hardware should be minimized. This makes the distribution model as open as possible, and, ideally, makes the act of mining a simple swap from electricity to ether at roughly the same rate for anyone around the world. Secondly, it should not be possible to make superlinear profits, and especially not so with a high initial barrier. Such a mechanism allows a well-funded adversary to gain a troublesome amount of the network's total mining power, and as such gives them a superlinear reward as well as reducing the network security. One plague of the Bitcoin world is ASICs. These are specialized pieces of compute hardware that exist only to do a single task. In Bitcoin's case, the task is the SHA-256 hash function. While ASICs exist for a proof of work function, both goals are placed in jeopardy. Because of this, a proof of work function that is ASIC resistant has been identified as the proverbial silver bullet. Two directions exist for ASIC resistance. Firstly, make it sequential memory hard, i.e. engineer the function such that the determination of the nonce requires a lot of memory and bandwidth such that the memory cannot be used in parallel to discover multiple nonces simultaneously. The second is to make the type of computation it would need to do general purpose. The meaning of specialized hardware for a general purpose task set is, naturally, general purpose hardware, and as such commodity desktop computers are likely to be pretty close to specialized hardware for the task. For Ethereum 1.0 we have chosen the first path. More formally, the proof of work function takes the form of POW. M equals H. N6 2256H. With equals POW, where Hn is the new block's header but without the nonce and mix hash components, H is the nonce of the header, D is a large data set needed to compute the mix hash, and H is the new block's difficulty value, i.e. the block difficulty from section 10. POW is the proof of work function which evaluates to an array with the first item being the mix hash and the second item being a pseudo-random number cryptographically dependent on H and D. The underlying algorithm is called Ethish and is described below. 1.5.1 Ethish. Ethish is the POW algorithm for Ethereum 1.0. It is the latest version of Dagger Hashimoto, introduced by Buterin and Dryja, although it can no longer appropriately be called that since many of the original features of both algorithms were drastically changed with R&D from February 2015 until May 4, 2015. The general route that the algorithm takes is as follows. There exists a seed which can be computed for each block by scanning through the block headers up until that point. From the seed, one can compute a pseudo-random cache, J-cache in bytes in initial size. Like clients store the cache. From the cache, we can generate a dataset, J-dataset in bytes in initial size, with the property that each item in the dataset depends on only a small number of items from the cache. Full clients and miners store the dataset. The dataset grows linearly with time. Mining involves grabbing random slices of the dataset and hashing them together. Verification can be done with low memory by using the cache to regenerate the specific pieces of the dataset that you need, so you only need to store the cache. The large dataset is updated once every JPEG blocks, so the vast majority of a miner's effort will be reading the dataset, not making changes to it. The mentioned parameters as well as the algorithm is explained in detail in Appendix J. 12. Implementing contracts. There are several patterns of contracts engineering that allow particular useful behaviors. Two of these that we will briefly discuss are data feeds and random numbers. 12.1 Data feeds. A data feed contract is one which provides a single service. It gives access to information from the external world within Ethereum. The accuracy and timeliness of this information is not guaranteed, and it is the task of a secondary contract author, the contract that utilizes the data feed, to determine how much trust can be placed in any single data feed. The general pattern involves a single contract within Ethereum which, when given a message call, replies with some timely information concerning an external phenomenon. An example might be the local temperature of New York City. This would be implemented as a contract that returned that value of some known point in storage. Of course, this point in storage must be maintained with the correct such temperature, and thus the second part of the pattern would be for an external server to run an Ethereum node, and immediately on discovery of a new block, creates a new valid transaction, sent to the contract. Updating said value in storage. The contract's code would accept such updates only from the identity contained on said server. 12.2 Random numbers. Providing random numbers within a deterministic system is, naturally, an impossible task. However, we can approximate with pseudo-random numbers by utilizing data which is generally unknowable. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 17. At the time of transacting, such data might include the block's hash, the block's timestamp, and the block's beneficiary address. In order to make it hard for malicious miners to control those values, one should use the block hash operation in order to use hashes of the previous 256 blocks as pseudo-random numbers. For a series of such numbers, a trivial solution would be to add some constant amount and hashing the result. 13 Future directions. The state database won't be forced to maintain all past state tree structures into the future. It should maintain an age for each node and eventually discard nodes that are neither recent enough nor checkpoints. Checkpoints, or a set of nodes in the database that allow a particular block's state tree to be traversed, could be used to place a maximum limit on the amount of computation needed in order to retrieve any state throughout the blockchain. Blockchain consolidation could be used in order to reduce the amount of blocks a client would need to download to act as a full mining node. A compressed archive of the tree structure at given points in time could be maintained by the peer network, effectively recasting the genesis block. This would reduce the amount to be downloaded to a single archive plus a hard maximum limit of blocks. Finally, blockchain compression could perhaps be conducted. Nodes in state tree that haven't sent/received a transaction in some constant amount of blocks could be thrown out, reducing both ether leakage and the growth of the state database. 13.1 Scalability. Scalability remains an eternal concern. With a general least state transition function, it becomes difficult to partition and parallelize transactions to apply the divide and conquer strategy. Unaddressed, the dynamic value range of the system remains essentially fixed, and as the average transaction value increases, the less valuable of them become ignored, being economically pointless to include in the main ledger. However, several strategies exist that may potentially be exploited to provide a considerably more scalable protocol. Some form of hierarchical structure, achieved by either consolidating smaller lighter weight chains into the main block or building the main block through the incremental combination and adhesion of smaller transaction sets, may allow parallelization of transaction combination and block building. Parallelism could also come from a prior-ethiced set of parallel blockchains, consolidating each block and with duplicate or invalid transactions thrown out accordingly. Finally, verifiable computation, if made generally available and efficient enough, may provide a route to allow the proof of work to be the verification of final state. 14 Conclusion. We have introduced, discussed, and formally defined the protocol of Ethereum. Through this protocol, the reader may implement a node on the Ethereum network and join others in a decentralized secure social operating system. Contracts may be authored in order to algorithmically specify and autonomously enforce rules of interaction. 15 Acknowledgements. Many thanks to Aaron Buchanan for authoring the Homestead revisions, Christoph Jentsch for authoring the Ethish algorithm, and Yoichi Hirei for doing most of the EIP 150 changes. Important maintenance, useful corrections, and suggestions were provided by a number of others from the Ethereum dev organization and Ethereum community at large, including Gustav Simonsen, Powell Bilica, Yoda Steiner, Nick Savers, Victor Tiaron, Marco Simovic, Giacomo Tazzari, and, of course, Vitalik Buterin. 16 Availability. The source.
I thought this was gonna be longer, to be honest. But I didn't realize that there's a lot of appendix. Maybe I should go over the appendix as well. I think I'm gonna stop here because I have a massive headache. I'm probably gonna go back to this at some point in the future. Not sure, but maybe. The thing that sucks the most about this and the white papers is that they use a bunch of different symbols that I'm not familiar with. So, but eventually I think it might be a good idea to look them up one by one, because I'm probably gonna see these symbols a bunch of times as I study more white papers, and even in machine learning, there's probably a bunch of similar symbols as well. Yeah, so I think I'm gonna stop here and probably look at this another time from the beginning again. So yeah, I'm gonna stop, and then I'm not sure what I'm gonna do next time. Maybe I'll do this, maybe I'll do something else. So yeah, so see you then.